Hey everybody, this is Mr. Conklin. I'm recording from my my basement studio, as I affectionately call it. I did just set up with a computer and a webcam here, and this is my pen. This is my hand. So hi, how you doing? There's also a cat here that's on the screen. Welcome to my house. And I just wanted to give you a couple of catch-up notes in case anybody didn't get it. This is going to cover three main things. Let me see if I can move this. Uh, this whole thing is balanced on a TV tray, in case you're curious. So it's a little bit unstable. But I want to cover three things. There were two theorems that we covered in class, and then there was a technique that I'll cover in a minute. Let me run these down real quickly. I think well the previous parts of the chapter. Let me just summarize these real fast. For this chat, I don't even remember what chapter it is. I think it's chapter 3 or chapter 4, whatever. It's going to be pretty much finding intervals. And hang on a second. I need to put my glasses on here so I can see what I'm doing. Okay, so intervals for height. I'll explain that in a minute. Um, Increasing and decreasing. Decreasing, I'm one of the world's slowest writers. Decreasing. It's also a weird angle to write on here. I'm sort of slouching over this TV tray here. And then there's one for concave up or down. Now, again, if you want to find out what heights are on a particular function, you do plus minus notation on plain old f of x, because f of x is the same as y, and that gives you the height of a graph. If you want to do increasing or decreasing, you want to find out where's the graph going up or where's the graph going down when you read from left to right. You do plus minus notation of f prime of x, because the first derivative is the tangent slope. So if the tangent slope is positive, it's going uphill. If the tangent slope is negative, it's going downhill. So whenever the first derivative is positive, it's increasing. Whenever the first derivative is negative, it's decreasing. So if you do plus minus notation, you'll see all the regions where they're positive or negative or positive or negative or what have you. And then concave up or down, you do plus minus notation of the second derivative, because that controls concavity. So if you find the second derivative is positive, you're going to have concave up. If you have the second derivative is negative, you're being concave down. Does that make sense? So here, sloping up and then sloping down would be positive and negative first derivative. And then above the x-axis is positive for height, and below the x-axis is negative for height. Does that kind of make sense? So that's kind of a summary of the first part of the chapter. So the last three things we wanted to cover are two theorems and a technique. So the first theorem is called Rawls' theorem. This theorem was made by a mathematician whose last name was Rawls. I honestly don't remember his first name. I feel I'm embarrassed on that one. Hang on a second. Let's see if I can focus this a little better. Come on, focus. That's a little better. Hopefully it won't do all the auto zooming, but whatever. Rawls' theorem. Now in geometry, you might remember that a theorem is something that's been proven. So any theorem in math is something that's been proven beyond all doubt. A theory is something, usually in physical science, that you think might be true, but it hasn't really been proven yet. But a theorem is something that has been proven, like the Pythagorean theorem. It's been proven like over 200 different ways. So Rawls' theorem is a little exotic. It basically says if f of x is, and there are three conditions for Rawls' theorem. If f of x is continuous on some sort of interval, let's call it from a to b, And A and B can be any numbers you want. Just make sure A is smaller than B. And I want you to do square brackets, which means that includes the ends. So if f of x is continuous on a particular interval from end to end, that means there are no breaks. I'll tell you what that means a little bit more in a minute. Differentiable, there's a fun word. Differentiable on, and this is going to be almost the same interval, but not counting the endpoints. Differentiable basically means you can take the derivative. The derivative exists. So the derivative doesn't blow up or get undefined or anything like that. So continuous from end to end and differentiable inside the interval. Let me kind of show you what I mean. Suppose I have a function that's just sort of wibble waving. Suppose I have some weird value of x. I'm going to call it a. A might be 2 or something like that. And then over here, they'll have another value, which I'll call b. So this interval, let me make these dots a little bit bigger so you can see. This interval right here, from here to here, is what we're looking at. So I don't really, this is f of x. I don't really care what happens outside of that interval. It could blow up or twist or flip around anything at once. I'm just looking just at this little interval. So it's sort of like saying, all right, Rawls' theorem is saying, look at this little interval and check, is it continuous from end to end? Are there any breaks? If there are no breaks, you're good to go. If there's a break, like a hole or a vertical asymptote or something, or a definition break, then you got a problem. Differentiable means their derivative exists every single point. So if I took the derivative here, it would exist, here it would exist, and so on, all the way inside, not counting the ends. You don't have to have a derivative there, but make sure the derivative exists in here. I'll talk more about that in a minute. And 3, this is going to seem a little abstract. F of A is equal to F of B, which basically means the ends are the same height. You may remember that when you plug in a value into a function, you get its height, like that's up here. So the height is the same as f of x, which is another name for y. But basically, if you plug a number into a function, you'll get its height, the original function. And that's what's going on here. So let's say here, I don't know what height it is. It might be 3, it might be 2, or it might be whatever. But I'm going to call this f, like the height here is f of A, but it's also the height of f of B. Like these 2 points just happen to have the same height. Like if I had somewhere different, like if this was C somewhere, the height would be way down here. So when you plug a value of x in, you'll get a value of y out, which is height. So 3 conditions. This interval has to be continuous from end to end, differentiable, that means the derivative exists inside that interval, and the 2 endpoints have to be the same height. If all 3 things are true, then Rawls, who lived hundreds of years ago, discovered then there must exist, that's great English, then there must exist, or there exists, at least one value of x. We call it x equals c for some like random, we already used a and b, so I figured I'd use it c. Like this is x equals a, this is x equals b. But it says that there's at least one value of x, that we'll call it x equals c, on the interval I'm actually going to say in the interval, because it not on the endpoints. In the interval, I suppose it could be on the endpoints, whatever, but definitely in the interval, such that f prime of c equals 0. That means that the derivative there is 0. Let me try and put this into plain English. All right, If you have a well-behaved function so that it doesn't blow up and the derivative doesn't go wacky, at least on this interval, and if you're lucky enough to have the two ends of the interval the same height, then this is saying there's at least one value in here somewhere where the tangent slope is 0. And as a matter of fact, it's probably right here. This is actually a pretty useful theorem for finding out whether it has a max or a min, or at least, or some weird spot where the derivative is 0, where it's flat. So this is pretty much saying if you're lucky enough to have something continuous and the derivative exists, because the derivative has to exist, otherwise you can't set it equal to 0. And if the two ends are the same height, there must be at least one place in between where the derivative is 0. There may be more than one, but there's at least one. That kind of makes sense? Now, let me talk about continuity for a second. Continuous. What does that mean? So that's a reference up here. That's a condition number 1. Continuous means that there are no holes, vertical asymptotes, or definition breaks. Whoops, what am I doing? Definition. Just in case you're wondering, this thing kind of wobbles. There's black metal under this thing and it kind of bends because it's kind of thin. So if I'm making you seasick by pressing this thing, I apologize. So no holes, vertical asymptote, or definition breaks. Now we know from past experience that holes are when you have, let's say, x minus 2 over x minus 2, where you have a division by 0. Like this would be a hole at x equals 2, and you could even find the location of it by plugging the x in. But basically, if you have a division by 0, that cancels. A vertical asymptote, we also know that it's a division by 0 that doesn't cancel over x minus 3. And let's say there's a vertical asymptote at x equals 3. Okay. Now, we've almost never talked about definition breaks until this point. There are basically 3 types of definition breaks you could ever run into. First would be a radical. Because when you take a look at the graph looks like a half parabola, but it stops dead in its tracks. Whoops, I should have y equals radical x. It stops dead in its tracks at 0, because if you try and go further left, you'd have x as negative, and square root of a negative is imaginary. You can't graph that at all. So that's interesting. It just stops dead in its tracks. A definition break basically means that the graph breaks. It either gets chopped, amputated off, or it snaps and continues somewhere else. So the first condition is if you have a radical somewhere. So I would say that there is a definition break at x equals 0 in this case, because that's just where the graph stops dead in its tracks. Number 2 is if you have something called a piecewise function. So let's say f of x equals equal to x if x is greater than 3, and 2 if x is less than or equal to 3. Just to give you an idea of what that would look like. We've seen some of these in the past. I sometimes nickname it a multiple personality function. It behaves one way when it's to the right of a boundary, and it behaves another way if it's to the left of the boundary. So it seems to be changing its behavior at x equals 3. So like right here, it'll behave one way to the right and another way to the left. So basically, if you could graph it as y equals x, which is a diagonal line, if x is greater than 3, so it would kind of look like this. So if you had that line y equals x going, it starts existing as soon as you get to the right of 3. So I draw something like that. And then it looks like y equals 2 if x is less than or equal to 3. And that looks like this. Here's y equals 2. And there's the entire graph. The graph looks strange for 2 reasons. Number 1, it's got this 2-part thingy going on here. And 2, you notice it snaps. It's discontinuous. That means it goes here, solid dot, and then it just snaps and then just continues here as if nothing had happened up here. but there's a gap. There's a one space gap here. That's called a definition break. I would say there's a definition break. There's a break in the definition of the graph at x equals 3. Okay. There is kind of a weird one also. Y equals, I could do f of x equals, but whatever. I don't know if you've ever seen this before, unless you were in the class where we did it. This is called the greatest. Your graphing calculator actually has this. Greatest integer function. On the calculator, it looks like this, INT. You'd have to go digging in some of the menus to find it. Oops, I'm sorry, I'm writing so low I didn't even see it. Let me do that again. Again, here, I think you were able to see that. Here's the new function, y equals, it looks like these sort of half brackets. This is called the greatest integer function. That means, well, let me show you. It means basically, you ask the question, what's the greatest integer? Well, I write very slowly, that x passed on a number line if you're reading from left to right. Let me explain that. Reading from, let me get done writing my slow stuff. Left to right, kind of getting a cramp by leaning over this thing here, but I love you guys, so I'm going to sacrifice for you. So reading from left to right. Just a second, I need to shake my hand out and get some blood in it. Okay, much better. So what's the greatest integer that you pass on a number line? What does that mean? Well, suppose I have the greatest integer of 2.3. These little brackets mean the greatest integer. So you're basically asking on a number line, so here's 0, and here's 2.3. If you read from left to right, what's the greatest integer that you've actually passed so far? It's 2. So if you say, what's the greatest integer of 2.9? Still 2, because you haven't passed 3 yet. You might say, is this rounding? Kind of. It's actually rounding down, not regular rounding. Regular rounding is if it's like 2.5, it rounds up. If it's 2.49, it rounds down. This is one that always rounds down no matter what. Like 2.9 would round down to 2. 2.999 would round down to 2. 3.01 would round down to 3, and so on. So this is a really kind of a weird function, but it's even a weirder graph. Let me show you. I'm not sure you're going to run into it, but just for as an experiment, think of the greatest integer of 2. Well, that rounds down to 2. So I know it has if I'm going to graph this, y equals the greatest integer of x. Let's try it. If x is 2, y is 2. If x is 1.9, that rounds down to 1. So like this is like 1.9 value x. 1.8 is still 2. 1.7 is still 2. 1.6 is still 2. 1.5, 1.4, all the way down to 1. So it looks like this. You can't use 2 because that's already up here. And then how about 0.9? That rounds down to 0. So you give it a height of 0. X is 0.8 has a height of 0. 0.7, 0.6. It turns out if you keep doing this over and over, you're going to get this kind of stair-step looking thing with solid dots on the left and open dots on the right. And it keeps going forever. But you notice this is one of the interesting examples where it's broken. There's a definition break all over the place. Every whole number, every round number, actually, integer. So I would say there is a definition break at every integer. I'll say every integer value of x. So lots and lots of definition breaks. So like x equals 1, x equals 2, x equals 3. Every single time you hit a round number, it breaks. Because over here at 2, look at that, snapped. Look at here, snapped. So these are the three basic cases where you might run into a discontinuity. So way, way back when, why on earth were we bringing this up? If f of x is continuous from here to here, that means there are no holes, no vertical asymptotes, no definition breaks. This whole blah, blah, blah was just to show you the three common cases where you'd run into a definition break. And in this class, you're probably not going to run into greatest integer function. Maybe you will. These two you may. Definitely you'll run into radical graphs, and you might run into piecewise functions. I might as well put the name here. This is a piecewise function. Piecewise function. Okay, so piecewise functions, they're not always discontinuous. Like if this thing had been lowered one space, it would have been lucky and just been continuous, but it's not. It actually snapped. So you actually have to lift your pen in order to keep drawing it. So, all right, back to the beginning. Is it continuous from here to here? You ask yourself, are there any holes? No. Are there any vertical asymptotes? No. Are there any definition breaks? No. Then the first thing is clear. It's true. Now, is it differentiable inside the interval, like not counting the ends? Well, good question. What does it mean to be differentiable? That means a derivative exists, but that means that there may be some cases where the derivative doesn't exist. There are actually 5 cases where the derivative doesn't exist. It's differentiable if there are no, there are 5 things. The good news is that you know 3 of them already. Holes, vertical asymptotes, definition breaks. Because if you destroy the original function, what am I doing? Wow, breaks, not breaky. If you destroy the original function, if the original function is discontinuous, there's no derivative there. There's just no way. You can't have a derivative at a very end. There's a little bit of controversy in math circles about that, but all the best books have said that even on an end that looks like it has a derivative, you don't. So if the graph just snaps, there's no derivative there. Pretty much it's because the derivative has to exist on both sides because it's a limit. And if the two sides don't agree, there's no limit. So no holes, no vertical asymptotes, no definition breaks. And there are 2 special cases which would destroy derivatives in addition to destroying the graph. So these 2 don't destroy the graph, but still make the derivative not exist. Something called a sharp turn. So sharp turns will make the derivative not exist. I'll show you that in a minute. And the 5th is called a vertical tangent. So vertical, what do I mean by this? So first of all, if I looked at the original graph, I'd say, when would a graph, I got this bug on my paper here. When would the graph not have a derivative? Well, obviously at a hole, because there's no place to take a derivative. Vertical asymptote, same thing, no place to take a derivative. And definition break, there's no place to take a derivative. You don't know which side, and it's broken anyway. Sharp turn, what does that mean? Well, looks like this. You can have a graph that looks like that. And at this very instant, there is no derivative here. Oops. Now, the reason behind that is that, remember, the first derivative is the slope. Watch the slope. It's going to be positive, 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 positive. And you see this side, the slopes are downhill. So it's negative, 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 negative. This side is saying, oh, the top must have a positive slope. And this side says, the slope must have a negative slope at the top. Well, they can't agree. And if you remember way back to chapter 1, if there's a limit that doesn't agree on the left and on the right, there's no overall limit. A derivative is a limit. You remember it's the limit as delta x approaches zero of x, f of x plus delta x, blah, blah, blah. That big limit definition of a derivative. Don't worry about it. But it was just remember that a limit, let me say it again, a derivative is a limit and it obeys the same rules, which means if the left side of a derivative and the right side of a derivative don't agree on a point, then there's no derivative at all. Right here, we honestly don't know what the slope is. It doesn't have one. And a vertical tangent, what does that mean? Every once in a while, you're going to get a graph that does this, that at a single instant, the graph slope is perfectly up and down. And if you remember from first year algebra, what's the slope of a perfectly up down vertical line? It's undefined. It doesn't exist. Because if you tried to do it, it's like rise over run is rise one, run zero. So the slope is 1 over 0, which I hope people have a problem with because you can't divide by 0. So the vertical tangent, there is no derivative here. That makes sense? Okay. Tell you what, I'm going to give you more of a, you're not going to notice much because I'm going to record the other part later, but I'm going to post these side by side on the website. My alarm's going off to shut this thing off. They only allow me to record an hour on this thing, so just welcome to my life again. But just as a summary, I wanted to give you an overview mainly of what does continuous mean, what does differentiable mean? Sorry, it's tilted, and how are the cases where you could be discontinuous or not differentiable? So continuity, that means if the graph's continuous, that can be destroyed by holes, vertical asymptotes, definition breaks. Derivatives can be destroyed by 5 things. Those first 3, holes, vertical asymptotes, definition breaks, but they can also be destroyed by sharp turns or by vertical tangents. Okay, so if you have this down pat, then we should be able to continue with Rawls' theorem in my next video, which you should be able to just click on the next video. I'm going to have to wait like 2 days. But you might hear, unless I get sick or something, you won't hear much difference in my voice. But God forbid. I think that's it. So see you in the next video. So take care. God bless. And if you're traveling, safe travels. Talk to you later. Bye-bye.